I want to start by just reflecting, where have we been, where are we going, and where are we right now? So we spent a huge amount of time on regular languages, right? And at this point, you should be comfortable with regular languages represented as a set, as a regular expression, as a DFA, as an NFA, and as a regular grammar. And we've also proven that some languages that are not regular, right? So we know there are some languages that are not regular. Those are languages that we can't represent with a regular expression. We can't draw an NFA for. So we're suddenly taking a big jump, and we're moving on to the next level. And we spent so much time on regular languages so that we could do everything in kind of really nitty-gritty detail on the simplest kind of language, so that you understand all the basics of the material that we're covering. And now we're moving on to the next level, okay? And now what we're going to do is we're going to talk about other kinds of languages. And we're going to do a lot of the same things that we did for regular languages, but I get to move a lot faster as I teach you for these things, because now you understand the idea of how a language can be a set and a regular expression and a DFA and an NFA and the equivalents and whatnot. So similarly, as we move on to the more complex kinds of languages, we will see that they have lots of different representations too. Okay? So what we're going to do now, because you have all these skills that we've built up over the semester, is we're going to talk about and we are going to prove things about much more complicated languages. And we're going to realize it's not so hard to do because we have such a good foundation in this material. Okay, so now we're going to talk about this new kind of language. We've been talking about regular languages, remember, forever. And now we're going to talk about languages that are context-free languages. Okay, so just to review, we've already shown that some languages, for example, a to the n, b to the n, where n is greater than or equal to 0, is not regular. How did we show that? We used the pumping lemma, right? Well, actually, what we did was we did a proof by contradiction that took advantage of the pumping lemma to help us find a contradiction, right? Now, we know that we can represent this a to the n, b to the n using a grammar, right? If you remember when we started learning about grammars, the first thing we did was we learned about grammars that were just generic grammars, not regular grammars, right? But just generic grammars. So we could write something like S goes to A, S, B, or lambda, right? And that will generate this language. This is not a regular grammar, right? We know that because there's this non-terminal right in the middle there. But it is a grammar, right? So a couple of weeks ago when we talked about grammars, we learned the term context-free grammar and the definition of a context-free grammar, right? And a context-free grammar is a grammar whose productions are of the form S goes to omega, where S is a non-terminal, so we only have one non-terminal on the left-hand side. And omega can be any string over the alphabet of terminals and non-terminals, right? So this is the kind of non-regular grammars. Remember, we talked about regular grammars versus context-free grammars before. And so we're just back into the world of context-free grammars because we're moving beyond regular languages. So here is my context-free grammar for a to the n, b to the n, right? It's what I wrote before, because of course you remember, I shouldn't use a double arrow because that means something in context-free grammars, right? Or in grammars in general. You remember that this expression here is really two rules just with a shortcut, right? So this is really one rule, S goes to lambda, and another rule, S goes to ASB, which is what I wrote before. I wrote them in a different order, but it's fine. So question one, is this a context-free grammar? You bet, right? It's got, on the left-hand side of all our production rules, they all have just a single non-terminal. And on the right-hand side, we have a string of terminals and non-terminals. That's fine. So, yep, it's a context-free grammar. And the next question is, are all regular grammars context-free grammars? And I hope that you will recognize already that, yes, regular grammars are a subset of context-free grammars, but all regular grammars are therefore context-free grammars. Not all context-free grammars are regular, right? I mean, this is not a regular grammar right here. Okay, this is just context-free. It's not regular, right? Because we have this non-terminal in the middle of a production rule on the right-hand side. But it's context-free, and if we take any regular grammar, that's also a context-free grammar. So yes, all regular grammars are indeed context-free grammars. Just like we have regular grammars and how they relate to regular languages, context-free grammars relate to a certain type of languages that are called context-free languages. And here what we're going to say is a language is a context-free language if it's generated by a context-free grammar. So if you can make a grammar for it that's a context-free grammar, then the language that that grammar generates is a context-free language. So again, here's a question. Are all regular languages context-free? And the answer is that yes, of course, all regular languages are indeed also context-free languages. Let's talk about why that is. Well, what is a regular language? Well, one way to say what a regular language is it's something that's generated by a regular grammar, right? If you have a regular grammar, then we know there's a regular language that corresponds to it, right? But if there's a regular grammar that corresponds to that regular language, then you could also generate it with a context-free grammar, because whatever this grammar is, the regular grammar is, it's by definition context-free, because all regular grammars are also context-free. But if you can generate it by a context-free grammar, that means that it is a context-free language, by our definition of what a context-free language is, right? Context-free language is one that's generated by a context-free grammar. Beautiful. So when we talked about regular grammars, we talked about what if you want to take the union of two regular languages that you happen to have two grammars for. How would you combine those grammars so that you get the grammar for the language that's the combination of the two? And it was a little tricky at times because we had to make sure that the new grammar that we generated was always regular. But in the case of context-free, it's really, really easy. So let's suppose that M is a context-free language, and that M's context-free grammar starts with the symbol A. So we're not using S, we're going to use A. And suppose that the letter N is another context-free language. And let's make sure that all of our non-terminals in N are different from the non-terminals in M, right? So that just says we use different capital letters for the two grammars. Easy enough. All right. And let's say that instead of using S for the start symbol for N's context-free grammar, we decide that we're going to use B just because we can, right? And furthermore, we're going to assume that S is some non-terminal that we haven't used in M or in N, right? Again, it's a non-terminal. We can use whatever the heck capital letter we want, okay? So if we want the context-free language that is represented by the union of those two context-free languages, right? I'll tell you it is also a context-free language, right? Taking the union of two context-free languages probably seems expected. You probably expect that it would be context-free, and in fact, yep, you're right. And how do you do that? Well, if you have one context-free language that starts with A, goes to whatever it is, and you have another context-free grammar that starts with A, another context-free grammar that starts with B, goes to whatever it is, right? If you want to, so here's one context-free grammar, and here's another one, and there's a whole bunch of rules in here potentially, and a whole bunch of rules in here. And what we said is, because of the things that we've written here, there's no non-terminals that these guys have in common, okay? So we can just take the union of that very easily by saying, all right, list all the rules for this first grammar, list all the rules for the second grammar, and add one more rule at the very top with a new start symbol that says S goes to A or B. So now, of course, you can follow either path. You can follow the A path to generate a string or the B path to generate a string, and you end up with M union N. Okay, and if we look at the language that is created by concatenating the language M in front of the language N, so we take one string from M, we concatenate it with one string of N, and the set of all those squished together languages is a new language, right? If M and N are each individually context-free languages, then, as you would expect, the concatenation of the two languages is context-free. And again, if we have, rule 1 that says A goes to, or excuse me, grammar 1 that says A goes to whatever, and then we've got a bunch of rules, and we have grammar 2 that says B goes to whatever, and then there's a bunch more rules. If we just create a new start symbol and we say S, our start symbol, goes to AB, and we take all these rules together, now we have a context-free grammar for the concatenated language represented by M and N. And this is something we couldn't do with our regular grammars, right? We couldn't have a rule like this one in our, when we were looking at regular grammars and we were looking at concatenation, because of course you can't have two non-terminals on the right-hand side in a regular grammar. But in a context-free grammar, it's fair game, so we're in good shape. And you'll find that the last rule for star is equally straightforward. If you already have a language M, right? So our language M, if you look at its grammar, it starts with A, and then there's all the rules, right? Then if we want to figure out what is M star, what's a grammar for that, you just create a new start symbol S, which goes to either AS, so as many copies of you as you want of this first rule here, right? Or lambda when you're ready to end. So this is very, very similar to when we combined regular grammars. If you if this slide has been the least bit tricky for you, go back to where we talked about regular grammars and go back and take a look at the piece of the lecture on how we combine regular grammars together to get a new grammar. The big takeaway from this slide, of course, is if you have two context-free languages, you can take the union of them, you can take the concatenation of them, or you can even star one of them, and the result is still a context-free language. So here's some problems that I got out of the previous edition of the book. I couldn't actually find anything quite like this in our current book in this chapter, but it's still useful to practice. It's problems we've more or less done before, but let's do them again just for review. So the first one here asks us to find a context-free grammar for the language A to the N, B to the N plus 2 for N greater than or equal to 0. So let's just take this and stick it up here in the corner, and I will write the language down here so that you can see what we're trying to do. So we're doing A to the N, B to the N plus 2, such that N is greater than or equal to 0. Right, that's the language we're trying to create a grammar for, right? And, what does this mean? This just means that every time, every string in our language has 2 more letter B's than it does A's, right? And so this is pretty straightforward, right? One way to do this is say, okay, I'm going to have my start symbol is going to go to A followed by 2 little b's. So we add those extra b's right away. And then we deal with the A to the N, B to the N part. So we'll say A goes to, remember we need to have it kind of grow outwards because we need the number of A's to match the number of B's and spread outwards. So we'll say A goes to AAB or lambda. Easy enough. All right, so let's see, can I squish that a little bit? So the next one says palindromes of odd length, right? And again, it's a language that we've done before, right? The first and last letter has to match, and all the intermediate letters have to match. So this is really very easy for our palindromes. We want something like this. Our start symbol, well, every time we can either have an A at the front with an A at the back, so we're growing outwards again, right? So we put an A at the front of the back, or, and I'm just going to do it on another line because I seem to have run out of space, we could have a B at the front and a B at the back. Or, since we want odd numbered palindromes of odd length, we need eventually not to end with a lambda, but to end with one more letter so that we finish. So I'll just say that my final thing is you could also go to an A or a B, right? So this is 4 rules written on 1, 2, 3 lines, as opposed to this piece up here, which was 3 rules written, I guess, on 2 lines, right? Okay, so let me squidge this one out of the way. And we'll do one more. I don't know if you can read this. The last one we need to do for the first problem is just all strings with the same number of A's and B's. So that's interesting because now it's not a palindrome per se. It's just we have the same number of A's as we do B's. So there's all sorts of ways that we could do this. So let's squidge that back down. So, you know, we can't do something like this one that we've done before because we need to allow the A's and B's to come in any order, right? So let me tell you how I think about this one. If we already have a string, right, or if we're trying to generate a string, one thing that we could do is we could put an A and a B right at the front of any string that we already have. Or we could put BA at the front of whatever string we have. But we might not want to add to the front of the string right now. We might want to add to the end of the string. So we could also say put an AB at the end of the string. And we could also put a BA at the end of the string. But so far we've only put the A's and B's next to each other, and maybe we want a string that has 5 A's followed by 5 B's. So the last thing that we need to do is we need to say, all right, well, what if I put an A at the front and a B at the end, or a B at the front and an A at the end? And that's all well and good, absolutely. Actually, though, the final thing I need to do is somehow have a way for this to end, right? So I'll just throw in a lambda. So again, just for convenience sake, I've put 2 rules on the same line in several places. But, you know, you could have all of this actually on one line. You could have it spread out on 7 lines. It just kind of depends what's most convenient for you at any given time. Okay, so let's squidge that down. That's always fun. Let's bring this guy up again. All right, so now it says find a context-free grammar for each of the following languages. Now see, look at this one here. This one is 2 languages concatenated with each other, right? So we're starting with A to the N, B to the N, and concatenating that with A to the N, B to the 2N. So this is 1A and 1B, right? So same number of A's and B's, I'm sorry. And this is twice as many B's as A's. And all the A's come first in here and then the B's. All the A's come first in here and then the B's. And so what I'm going to do is I'm just going to use that trick that we talked about in a recent slide. I'll make a context-free grammar for each of those, and then I will concatenate them together. So let me just move these things way out of the way. Maybe shrink them super tiny so we have a little bit more room to work. Okay. So first I'm going to do my grammar for A to the N, B to the N. And maybe I won't start with S, I'll start with A for a change. So I'm going to say A goes to AAB or lambda, right? That gives me A to the N, B to the N, the same number of A's as B's. And then I want another grammar that maybe I will start with a B that gives me 2 B's for every A. So that is A, B, and 2 little b's, or lambda. And to make this the concatenation of the two, I just create a start rule that looks like that. And magic, this is the language that that we saw in here, right? This is these two languages concatenated together, right here. Terrific. The second one it asks us to do, before I shrink this down again, is just A to the N, B to the M, where N is bigger than M. So we always have more A's than B's, but we don't know how many more. Okay? So let me do some rearranging here. Let me shrink this down a bit. Let me take this purple guy and put it out of the way. So now we're trying to do a language, remember, that has an arbitrary number of A's and B's. We just got to make sure that we always have more A's than B's. Okay? Or equal. It could be equal. Okay? So what I'm going to do is I am going to do A to the N, B to the N, our standard old favorite language where I do something like S goes to A, S, B, right? And this is going to give us a language that has the same number of A's and B's. And then what I'm going to do is I'm going to give myself an out, and I'm going to say, or you can jump to this other thing. So once you've got a string that has as many A's as B's, so you have the same number of A's and B's, then we'll go to this new production rule. And this new production rule is going to add as many more A's as you want. So I'm going to say B goes to AB or lambda. And if you take a look at this language, I think you'll see that what you get is you start out by coming up with as many A's as you have B's, and then you add as many more A's as you want on there. So, pretty good.